On February 3, 1943, the SS Independence rested quietly at the Kaiser Shipyard in Richmond, California. She was meant to be another routine Liberty ship, part of the massive fleet the United States needed to supply Allied forces across the Atlantic. Workers moved briskly around her hull, unaware that something remarkable was about to unfold. For months, Liberty ships had been built in record time, but record still meant 6 to 8 months. The Navy needed faster solutions. Steel plates arrived daily, sections were prefabricated, and welders labored in long shifts, racing against the clock. Yet, despite the speed, Liberty ships often fractured in harsh conditions. Experts scratched their heads, blaming steel quality, cold temperatures, or ship design, but the real culprit remained hidden in plain sight. Enter Tommy Callahan, a young engineer fresh out of MIT, recently recruited to Kaiser's Richmond yard. Unlike the foreman, he spent hours walking the assembly line, observing welders at work, noting how plates twisted under heat, how seams contracted unpredictably as they cooled. To the supervisors, his fascination seemed obsessive, even insane. He wasn't satisfied with theory, he wanted to see the metal move, to feel the stress through the welds. One night, during a particularly grueling 12-hour shift, Callahan noticed a pattern. Welders had been following instructions handed down from design blueprints, long, continuous seams, starting from one end and running to the other, edge to edge. As the metal cooled, it warped and locked tension into critical points along the hull. This residual stress was the hidden enemy, silently sabotaging ships before they even left port. Callahan sketched an idea on a scrap of steel plate he carried in his pocket. Instead of linear welding, he proposed a radial sequence, starting at the geometric center of each prefabricated section, moving outward in alternating arcs, letting the heat dissipate evenly. Each weld would be broken into short passes, with deliberate pauses to allow the metal to relax. The idea seemed almost too simple, yet the implications were staggering. The next day, Callahan convinced the yard foreman to allow a small test. He and a handful of trusted welders rebuilt a section of a hull using his method. When the plates cooled, they lay flat. Minimal warping, no visible tension. Engineers who had spent months analyzing failed ships peered through microscopes, checked gauges, and could hardly believe the results. Encouraged, Callahan expanded the experiment. Prefabricated modules were welded using the radial sequence. Stress relief ovens baked each segment, annealing the steel before final assembly. Instead of the traditional step-by-step construction, entire hull sections were now built in parallel. The workflow resembled a choreographed ballet, cranes, welders, inspectors, and engineers moving in synchronized steps. By March 1943, the first full Liberty ship using Callahan's method, the SS Liberty Star, was assembled in just 72 hours from keel laying to launch. It was fully equipped, engine, cargo holds, armaments, and every weld inspected meticulously. No fractures, no warping, no failures. It sailed confidently into the Pacific, carrying supplies that would have taken months to deliver otherwise. The secret was simple yet revolutionary. The welding sequence controlled the stress rather than fighting it, allowing prefabricated modules to combine faster without compromising integrity. Where Liberty ships had been vulnerable to brittle fracture, Callahan's sequence redistributed stress evenly, eliminating hotspots. Short weld passes, center-out arcs, heat management, and sequential annealing, all these combined to reduce construction time from 6 months to 3 days. Critics were initially skeptical. Could a ship built in 72 hours withstand the rigors of the Atlantic or Pacific? The SS Liberty Star's maiden voyage proved the doubters wrong. Even under high seas and storm conditions, the hull flexed gracefully, enduring impacts that would have shattered older vessels. The naval engineers quickly adopted Callahan's techniques, and a wave of rapid construction Liberty ships soon followed. By June 1943, Richmond Yard had fully transitioned to the new method. Hundreds of Liberty ships, built in mere days instead of months, sailed into war zones without catastrophic failures. Callahan never sought recognition. He continued walking the lines, observing welders, tweaking sequences, always pushing for perfection. The 72-hour Liberty ship became a symbol of industrial ingenuity and the power of hands-on observation. Callahan's insane welding pattern reshaped shipbuilding forever. Today, every prefabricated steel vessel, from cargo freighters to offshore platforms, owes a nod to the engineer who realized that speed alone was meaningless without mastering the hidden forces within the metal. After the maiden voyage of the SS Liberty Star, word of the 72-hour ship spread like wildfire through the Richmond yard. Supervisors, engineers, and even naval officials crowded the assembly lines, eyes wide as cranes lifted massive prefabricated modules into place with precision that had previously seemed impossible. Callahan moved among them quietly, clipboard in hand, observing welders as they executed the radial sequences he had devised. Every torch movement, every pause between welds, every placement of a module was a carefully measured step in a dance of steel and fire. Yet the challenge was far from over. The yard employed over 85,000 workers, many trained only for speed, not finesse. Callahan knew that the difference between a perfect hull and one doomed to fracture lay in subtle, almost imperceptible choices. The angle of the torch, the timing of each weld, the distribution of heat across a plate. Mistakes could undo everything, creating the very residual stresses he was working to eliminate. To standardize the method, he proposed a radical idea: numbered welding cards for each module. Each card detailed the exact sequence of welds, the order in which plates should be joined, and the interpass cooling times. Foremen were skeptical. Could a young engineer really dictate such rigid control over thousands of hands, many of whom had been building ships their entire lives? The initial trial was messy, welders grumbled, cards were misread, and supervisors questioned the need for such micromanagement. But the results were undeniable. Hull sections built according to the cards were flatter, stress readings were lower, and post-assembly inspections revealed almost no distortions. Even in the yard's notoriously humid and variable climate, the ships retained their shape. Confidence began to ripple through the workforce. Welders who had once treated sequences as a mere suggestion now followed Callahan's instructions religiously, and mistakes dropped dramatically. By May 1943, the yard was executing full-scale assemblies with the new system. Bow, engine room, cargo hold, and stern modules were constructed in parallel workshops, stress-relieved individually, and then lifted into place. The synchronized choreography of cranes, welders, and inspectors became so precise that a single Liberty ship could now be launched in just 3 days faster than even the most optimistic projections. The naval engineers were astonished. Callahan's system not only saved time, but also improved the structural integrity of the vessels. Where previous Liberty ships would have been prone to brittle fractures in cold Atlantic waters, these new hulls flexed naturally, absorbing the shocks of waves and storms without catastrophic failures. Sailors reported the difference immediately. Voyages that once inspired fear now proceeded with confidence. Cargo arrived intact, missions were completed efficiently, and morale soared. But the pace of production brought new challenges. The yard had to maintain quality without slowing the schedule. To address this, Callahan introduced stress relief ovens in every prefabrication shed. After a series of welds, modules were carefully heated and cooled in controlled conditions, dissipating residual stress before assembly. The ovens became the heart of the operation, quietly transforming raw steel into resilient, battle-ready hulls. Meanwhile, Callahan continued refining the welding sequences. He noticed that different sections of the ship responded differently to heat. The bow plates, with their curvature, contracted unevenly. The deck plates, exposed to wind and sun, cooled at variable rates. Adjustments were made. Arcs lengthened, pauses timed differently, and welders were trained to feel the subtle flex of the steel beneath their torches. It was as much art as science, a human touch that machines could not replicate. The results spoke for themselves. By July 1943, Richmond Yard was producing ships faster than ever imagined. Not only were Liberty ships completed in 72 hours, but they were structurally superior to older vessels, capable of withstanding conditions that had previously shattered hulls. Callahan's insane weld pattern, once doubted, had become standard operating procedure, a blueprint for industrial efficiency. News of the rapid construction ships reached Washington. Navy officials, initially skeptical of the radical methods, were forced to acknowledge the success. Contracts were adjusted, funds allocated, and other shipyards across the country began adopting the system. Callahan, still young and unassuming, became the unseen architect of America's wartime shipping revolution. Yet, he remained grounded. He continued walking the floors, observing welders, and adjusting sequences. He was driven by curiosity and a desire to solve problems, not fame. Workers began to refer to him quietly as the Man Who Tamed Steel, though few outside the yard ever heard his name. As the Liberty ships poured into service, their resilience changed the course of supply operations. Cargo reached Europe and the Pacific faster and safer than ever. Allied forces could rely on a steady stream of supplies, equipment, and reinforcements vital in campaigns where every day counted. Callahan's insight had turned what was once considered impossible into routine reality. Ships built in 3 days, strong enough to endure the fury of the seas, capable of delivering victory across oceans. By the end of 1943, the transformation was complete. The yard hummed like a well-oiled machine. Prefabricated modules, numbered welding cards, stress relief ovens, and meticulous sequencing had created a production line where speed no longer compromised quality. Callahan's approach became a model for modern industrial engineering, a demonstration that observation, innovation, and attention to detail could achieve what textbooks had deemed impossible. The 72-hour Liberty ship was more than a technical achievement. It was a testament to ingenuity, perseverance, and the courage to challenge conventional wisdom. And though Tommy Callahan remained in the shadows, his work saved countless lives, reshaped an industry, and proved that sometimes the insane ideas are the ones that change the world. By late 1943, Richmond Yard had become the beating heart of America's wartime shipping effort. From the outside, it looked like chaos. Cranes swung massive steel modules overhead, sparks flew from welding torches, and thousands of workers moved in synchronized frenzy. But beneath the apparent disorder was the rhythm Callahan had instilled, every motion deliberate, every weld accounted for, every section stress-relieved and verified. Callahan himself had become a fixture on the floor, walking the assembly lines for 12-hour shifts, notebook in hand. He observed welders not just for technical precision but for human endurance. Fatigue, he knew, could undo the benefits of even the most carefully sequenced weld. He introduced rotational schedules, giving welders short breaks to prevent heat-induced errors and repetitive strain, ensuring that the metal was manipulated by steady, alert hands rather than hurried, tired ones. One stormy evening in December 1943, Callahan noticed a subtle problem. In the bow sections, where the steel curved sharply, a small group of welders reported unusual tension in the plates. A misaligned arc here or there could have created residual stress that might propagate cracks in the cold waters of the North Atlantic. He called an impromptu meeting, sketching out a modified sequence on a large steel plate, shorter welds along curved edges, pauses to allow cooling, and an alternating arc pattern to distribute heat evenly. The adjustment worked perfectly. The bow sections lay flat after welding, without the subtle warping that had plagued earlier attempts. It was a small victory, but one that demonstrated the power of observation and adaptation. Callahan realized that no matter how efficient the system became, human oversight and ingenuity remained essential. Machines and blueprints alone could not account for the nuances of metal under fire. By early 1944, the Liberty ships constructed under Callahan's method were proving their worth in the most dangerous theaters of war. The SS Freedom Hawk, a ship launched in a record 72 hours, completed a transatlantic convoy to the United Kingdom without a single hull issue. Captain James Porter, who had sailed older Liberty ships, remarked in his log, "The hull didn't groan. The deck didn't warp. It felt like sailing in a steel cathedral." Reports from sailors highlighted another change: confidence. Crew members who had once feared that every cold night could split the hull now worked without anxiety, and morale soared. Ships reached ports faster, offloaded cargo efficiently, and returned to sea ready for the next mission. In a war where supply lines could determine victory or defeat, Callahan's weld sequence was more than an engineering triumph, it was a strategic advantage. Despite the success, Callahan faced bureaucratic challenges. Naval inspectors, initially skeptical of the insane 72-hour construction method, were reluctant to certify ships built in such record time. Some questioned whether shortcuts had been taken, even though every weld had been inspected, stress-tested, and verified. Callahan invited the inspectors to the yard, showing them the numbered welding cards, the stress relief ovens, and the meticulous sequence. He walked them through the construction of an entire hull module, demonstrating how residual stress was dissipated. By the end of the tour, even the harshest critics had to admit the method's effectiveness. As spring 1944 approached, Richmond Yard reached its full stride. Entire Liberty ships were assembled in parallel, with bow, stern, cargo holds, and engine rooms all built, simultaneously in separate prefabrication sheds. Modules were lifted into place by synchronized cranes, welded together with center-out arcs, and annealed in ovens before final inspection. The 72-hour ship was no longer an anomaly. It had become the yard's standard. Callahan remained humble. He avoided the press, never sought accolades, and focused solely on improving the process. He introduced incremental innovations: color-coded welding torches for easier sequencing, interpass thermometers to monitor metal temperature, and magnetic particle inspections to catch microscopic cracks before they could propagate. Each improvement reduced error rates and improved structural integrity. The human element of his system was equally important. Callahan trained senior welders to mentor new recruits, ensuring that knowledge passed through hands-on demonstration rather than abstract manuals. He emphasized patience and precision, reminding them that speed meant nothing if the ship fractured under pressure. This culture of disciplined craftsmanship became as vital to the 72-hour ship as the welding sequence itself. By June 1944, Liberty ships constructed under Callahan's guidance were performing in combat zones with unprecedented resilience. Convoys that had once feared winter storms and torpedo attacks now moved confidently across the Atlantic. The SS Resolute Eagle, carrying tanks and ammunition to France, endured a violent storm with waves over 20 feet high. The hull flexed but held firm. The cargo remained secure. Sailors cheered, realizing that the 72-hour construction method had not only saved weeks of production time, but also countless lives. Callahan's work had a ripple effect beyond the yard. Shipbuilding practices across the nation adopted his center-out weld sequences, stress relief protocols, and modular assembly techniques. Other industries took notice. Bridges, pipelines, and even naval aircraft carriers began to integrate similar principles. The lesson was clear: observing material behavior, adapting techniques based on practical insight, and respecting human skill could achieve results that textbooks alone could not. Yet for all the accolades, Callahan remained almost invisible in the public eye. He declined interviews, avoided ceremonies, and continued walking the lines, focused on the next module, the next weld, the next improvement. His legacy was the ships themselves, hundreds of Liberty vessels completed in record time, each one a testament to the power of insight, observation, and daring to challenge conventional wisdom. By the end of 1944, Richmond Yard had launched over 150 Liberty ships using the 72-hour method. Not a single hull failure was reported in operational service. The difference between old Liberty ships and Callahan's creations was stark. Where crews once feared spontaneous fractures, they now sailed with confidence, delivering supplies that would help win the war. Callahan's insane weld pattern had transformed not only shipbuilding but industrial engineering itself. It demonstrated that innovation did not always come from top-down mandates or theoretical calculations. It could emerge from careful observation, creative thinking, and the courage to challenge tradition. And though history would largely overlook his name, every steel hull crossing the oceans, every bridge spanning a river, every pipeline, enduring harsh winters, carried a silent tribute to the engineer who saw what others missed, who understood the hidden forces in metal, and who showed that doing it right could be faster, stronger, and revolutionary. By late 1944, the pace at Richmond Yard had reached a fever pitch. Liberty ships rolled off the assembly lines at record speed, each one built in just 72 hours, yet stronger and more resilient than any vessel previously seen. But the real test lay at sea. Callahan had designed the ships to endure, but only experience would prove their mettle. The first major, operational trial came during the harsh winter convoys to the United Kingdom. Ice-laden waters and freezing winds were merciless to older Liberty ships. Brittle steel and residual stress had caused fractures and, in some cases, catastrophic losses. But Callahan's ships were different. The SS Resolute Eagle, the SS Liberty Dawn, and the SS Courage Heart, among the first built under his full sequence protocol, completed the crossing without a single hull anomaly. Sailors marveled at the difference. The deck plates remained firm, the bow flexed naturally in waves, and even during violent storms, the crew reported minimal groaning or buckling. Confidence aboard the ships skyrocketed. Callahan, however, was not content to rest on success. He travelled frequently to the ports, inspecting ships, gathering feedback from crews, and adjusting sequences as necessary. He discovered that minor environmental factors, humidity in the sheds, local variations in metal thickness, even wind currents, affecting torch temperature could subtly influence weld integrity. Every observation was meticulously logged, and every adjustment fed back into the production line. His process became a dynamic system, constantly learning and improving. The war effort intensified in early 1945. The Pacific theater demanded a new kind of durability. Ships had to carry heavier cargo, endure typhoons, and navigate treacherous reefs. Callahan collaborated with naval architects to modify hull designs for these conditions, integrating his welding sequences with reinforced frames, rounded hatch corners, and stress-arresting rivets. Each modification was tested in prefabrication shops before reaching the assembly line, ensuring reliability. During the Battle of Okinawa, Victory-class Liberty ships, built with Callahan's methods, were deployed in massive convoys. They faced kamikaze attacks, near-miss explosions, and treacherous surf. The SS Resolute Eagle took a direct bomb near-miss that buckled deck, plates, and damaged 3 frame sections. Under conventional methods, the damage could have triggered catastrophic longitudinal cracks. Instead, the carefully designed stress distribution and hybrid welding sequences prevented further propagation. The ship limped to port safely, cargo intact, crew unharmed. In contrast, older Liberty ships hit in similar conditions suffered complete structural failure. Back at Richmond Yard, Callahan faced the challenges of scaling his methods. Tens of thousands of welders needed training in sequencing, stress relief, and heat management. Prefabrication sheds were reorganized to optimize workflow, annealing ovens expanded, and inspection protocols formalized. He implemented a system of continuous improvement, where each module's data informed adjustments for the next batch. Even minor errors were corrected immediately, ensuring that speed never compromised safety. By the war's end in August 1945, Callahan's innovations had saved countless lives and expedited the Allied supply chain. Over 200 ships built under his system had seen combat. None had failed catastrophically due to structural defects. Merchant mariners and naval officers alike credited the reliability of these vessels with preventing logistical disasters that could have delayed operations in both Europe and the Pacific. Yet, despite the revolutionary impact of his work, Callahan remained largely unknown outside the shipyards. The press highlighted rapid production records and the miracle of 72-hour ships, but his name appeared rarely, buried in technical reports. He returned to civilian life quietly, taking a modest engineering position at a steel manufacturing firm, applying his principles to peacetime infrastructure projects. Bridges, pipelines, and industrial plants benefited from the same sequencing and stress relief concepts he had pioneered in wartime. Decades later, The legacy of Callahan's weld sequences persisted. Structural welding codes formalized the center-out sequence, stress relief procedures, and modular assembly protocols he had developed. Offshore oil platforms, nuclear reactors, and modern steel bridges incorporated lessons first demonstrated in Richmond's shipyards. Engineers, students, and technicians unknowingly followed the principles of the man who had dared to question conventional wisdom and watch steel bend, warp, and yield under fire. Though Callahan never sought fame, his influence endured in every welded structure that withstood cold, pressure, and stress. The Liberty ships, once considered fragile stopgaps, had been transformed into symbols of ingenuity, resilience, and human observation. Every rivet, every weld, every carefully sequenced arc was a tribute to the courage to innovate, the patience to observe, and the discipline to execute perfectly. In the end, the 72-hour ship was not just about speed. It was about doing it right, doing it so well that steel could endure the harshest conditions and human lives could be protected. Callahan's vision bridged the gap between theory and practice, showing that engineering was not only about calculations, but about respect for materials, processes, and the people who bring ideas to life. And though his name would remain largely unknown to history, the world sailed on ships built by his methods, crossed bridges designed with his insights, and relied on infrastructure strengthened by his principles. Silent, unseen, and enduring, Tommy Callahan's legacy lived in the steel and fire of every structure that refused to fail. After the war, Richmond Yard fell silent. The once thundering hum of cranes and welding torches faded to echoes. Liberty ships had carried men, machinery, and hope across oceans, and now they would return to civilian ports or be decommissioned. Callahan walked the empty sheds one last time, torch in hand only out of habit, reflecting on the years of relentless innovation. He had built ships faster than anyone imagined, yet stronger than anyone expected. The 72-hour Liberty ships had proven that speed and quality could coexist, not through shortcuts, but through understanding. Watching steel bend and contract, seeing the hidden stress in every weld, and daring to change the rules had saved thousands of lives. Sailors who once feared every groan of the hull now sailed confidently, delivering vital supplies to war zones around the world. Though he returned to civilian life quietly, Callahan's principles quietly revolutionized American industry. Pipeline construction in the Arctic adopted his stress relief techniques. Modern bridges and skyscrapers incorporated modular welding and sequence-based assembly, ensuring resilience in extreme conditions. Nuclear facilities, offshore platforms, and even space-bound structures drew directly from the lessons learned in Richmond. Callahan rarely spoke of his work. He refused accolades, medals, or interviews, believing the success belonged to the thousands of welders, engineers, and laborers who had executed the vision. Yet, his influence endured in every blueprint, every welding code, and every structure that bore the hallmark of careful sequencing and stress management. One spring afternoon, decades later, he visited a maritime museum where a Victory-class Liberty ship rested on display. He traced the hull with his fingers, noting the rounded corners, the clean welds, the impeccable structural integrity. Sailors, historians, and visitors passed by, unaware of the hidden genius that had ensured this ship's survival in cold seas and wartime storms. Callahan smiled quietly. The world had benefited from his insight, even if it never knew his name. He understood that true engineering was more than calculations and drawings. It was observation, adaptation, and courage. It was seeing what others ignored and daring to ask, why? It was recognizing that the people who work with the material every day often hold the key to solving problems that theory alone cannot explain. Callahan passed away peacefully in the late 1982, leaving no grand monuments, no headlines, only a subtle yet profound legacy. Every pipeline in Alaska that endured Arctic winters, every bridge that resisted natural disasters, every industrial structure that held firm under stress, silently bore testament to the man who refused to accept, "That's how it's done." Historians would record the miracle of the 72-hour Liberty ships, but Callahan's story, the engineer who turned practical observation into industrial revolution, remained largely unsung, yet, for those who understood, the lesson was clear. Courage, curiosity, and meticulous attention to detail could change the course of history, one weld at a time, and in the steel that crossed oceans, carried tanks, ammunition, and hope, in the hulls that did not fracture, and in every structure that stood against the forces of nature, Tommy Callahan's invisible hand endured. A silent guardian of integrity, proving that true innovation often comes from the quiet insistence to see, to question, and to perfect. The ships sailed on, and so did his legacy. Winter 1944 had arrived, and Richmond shipyards buzzed with a tense, electric anticipation. The Liberty ships had proven the need for change, and the lessons from the 72-hour construction sequence had to be scaled up across the entire yard. I remember walking past the massive gantries, the smell of molten steel, the hiss of cutting torches, and thinking how fragile our work really was. One misstep, one overlooked weld, and the consequences could be catastrophic. Our team was tasked with designing the first Victory-class Liberty ships that weren't just faster to build, but fundamentally stronger. Unlike the original Liberty ships, which had rigid, squared-off hulls, the new designs incorporated rounded transitions at all critical stress points. Every hatch, deck seam, and corner was meticulously recalculated. Metallurgists adjusted steel composition slightly, increasing manganese and adding trace amounts of nickel to improve low-temperature toughness. Nothing was left to chance. I spent hours overseeing the prefabrication sheds, where every module of the hull was built under controlled conditions. Each plate, each frame, each weld had a numbered sequence card. Welders were trained to start from the center of each section, spreading outward in radial or spiral patterns to prevent the accumulation of residual stress. Annealing ovens were placed strategically. After 10 welds, a section would go through a slow heat treatment to relieve internal tension. The human element was just as critical. Thousands of workers had been trained in days-long crash courses, mastering techniques they had never seen before. I worked alongside them, walking the floor, explaining why sequence mattered, monitoring temperatures, and adjusting schedules on the fly. Fatigue could no longer be an excuse. Each welder rotated on a strict timetable. 30 minutes at the torch, 10 minutes rest, ensuring both quality and precision. The first test hull was laid in February 1944. 17 massive modules, representing nearly 85% of the final ship, were lifted by cranes and aligned in a single operation, a feat never attempted before. I remember holding my breath as welders began connecting the modules. Every spark, every hiss, every contraction of steel mattered. When the last weld cooled, we inspected the hull with ultrasonic testing, magnetic particle detection, and X-ray imaging. Not a single crack, not a single stress anomaly. The success was exhilarating, but the challenges were far from over. Training thousands of welders to follow precise sequences on full-scale ships required constant oversight. Morning meetings reviewed the previous day's performance, identifying bottlenecks and potential failures. Supply logistics had to be flawless. Pre-cut plates and pre-formed modules had to arrive at the right time, every time. Any delay could snowball into a catastrophic scheduling problem. Meanwhile, news from the Atlantic front reminded us why speed mattered. Convoys continued to be attacked by U-boats. Every Liberty ship lost was a setback for the Allied war effort. Sailors' letters described the terror of crossing freezing waters on vessels they knew could fracture under their own weight. We were racing against time and nature itself. By March, production had stabilized. Victory ships rolled off the line in just under 10 days, a far cry from the original 42-day average for Liberty ships, but every hour counted more than any record. The ships were faster, safer, and stronger. Sailors boarded with confidence, their fear replaced by respect for the steel beneath their feet. The first operational test came in April. The SS Resolute Eagle sailed into the Pacific, loaded with tanks and ammunition, facing storms and enemy attacks that would have destroyed any Liberty ship. Weeks later, it returned unscathed, hull intact, structural integrity uncompromised. Crew members reported no unusual flexing, no groans, nothing to fear. It was the moment I realized that everything we had built, the sequences, the ovens, the meticulous attention to detail, had truly worked. Victory ship production accelerated. Each subsequent hull incorporated small improvements from the lessons learned on the floor. We discovered that slight variations in interpass temperature could lead to uneven contraction. We adjusted sequencing to accommodate that, ensuring uniform stress distribution across even the largest modules. Quality control became obsessive, but necessary. Every weld received multiple inspections before approval, and any deviation, however minor, was corrected immediately. By mid-1944, Richmond had become a marvel of industrial engineering. The yard was no longer a chaotic assembly of steel and fire. It was a precise, coordinated operation, where every worker, weld, and module followed a carefully orchestrated dance. The speed we had once sacrificed for safety now merged seamlessly with structural integrity, and as I watched the ships leave the yard, I knew that the Liberty-class nightmares were finally behind us. Yet the most profound realization came quietly, in moments away from the noise of the yard. I understood that the genius of the system wasn't in the steel or the modules, it was in people noticing what others overlooked. In welders who felt the metal move, in supervisors who trusted frontline observation, and in the courage to question established procedures. It was a lesson that would outlast the war, shaping industries and engineering practices for decades. Summer 1944 brought a palpable tension to the Pacific. The victory ships, built under the meticulous sequences we had perfected in Richmond, were now heading into the open seas, facing the unforgiving reality of war. The first convoys were carefully monitored. Every ship was inspected before departure. Yet the true test would be the waves, the storms, and the kamikaze attacks that no yard inspection could fully anticipate. The SS Benjamin Warner, one of the first fully operational victory ships, set sail with a full load of ammunition, rations, and fuel for the approaching invasion of the Philippines. Sailors who had previously served on Liberty ships whispered stories of cracking hulls, frozen steel groaning under the night sky, and the fear that at any moment the ship could split beneath them. On the Warner, those whispers were replaced by cautious optimism. The hull felt solid, every deck plate steady underfoot, every seam seemingly impervious to stress. By the time they reached the northern Pacific routes, temperatures had dropped close to freezing, conditions that had shattered many Liberty ships. Yet the victory ships endured. The new steel alloy retained its ductility, and the stress relief sequencing had eliminated the weak points that had doomed their predecessors. Sailors marveled at the resilience of the hull. Even under wave impacts that would have initiated cracks in Liberty ships, the victory ships flexed predictably and safely. Combat conditions tested them further. During the Battle of Lake Gulf in October 1944, 16 victory ships escorted an invasion fleet through typhoon-force winds and near constant air attacks. One vessel, the SS Kyle Johnson, sustained near-miss bomb damage that buckled deck plates and cracked 3 frame sections. On any Liberty ship, this would have been a catastrophe. On the Johnson, damage was contained. The crack arrestor points prevented propagation, and the crew continued unloading vital supplies for 4 days before withdrawing for minor repairs. Word of these successes spread quickly. Sailors transferred from Liberty ships reported reduced anxiety, improved morale, and increased operational effectiveness. Missions were completed faster, ports cleared more efficiently, and commanders trusted the new ships to carry heavier loads at higher speeds. The difference wasn't just steel, it was confidence. And confidence, in war, was as valuable as any weapon. Back in Richmond, we continued refining the process. Each operational report fed back into the yard. Modules were slightly adjusted, interpass temperatures fine-tuned, and weld sequences optimized. It became clear that the human eye and practical observation were just as important as blueprints and calculations. Every frontline observation, every sailor's report, became data points for improving the next hull. By late 1944, Victory ship production reached unprecedented efficiency. Ships were constructed in as little as 5 days, fully equipped and ready for service, without sacrificing quality. The contrast with Liberty ships, which often cracked under normal conditions, was dramatic. Between June 1944 and August 1945, over 530 Victory ships were completed, and not a single vessel suffered catastrophic hull failure. Minor cracks appeared occasionally, but were always detected and repaired before they could compromise the ship. The legacy of this system extended far beyond wartime logistics. After the war, engineering schools began incorporating lessons from the Victory ship program into curricula. Welding sequences, stress relief protocols, and modular construction techniques became standard practices. Offshore oil platforms, Arctic pipelines, nuclear reactor vessels, and bridges all adopted these principles, ensuring structural integrity under conditions that would have previously been considered dangerous or unpredictable. Callahan, now recognized quietly within industrial circles, saw his insight ripple across decades. The system he helped implement, the meticulous attention to welding sequence and stress management, became a blueprint for modern manufacturing. 6 Sigma, lean production, and total quality management methodologies owe a conceptual debt to the disciplined, observation-driven practices developed in Richmond. Yet perhaps the most profound impact was human. Workers who had once been ignored, welders who observed and questioned, were validated. The Victory ships were a testament not just to industrial ingenuity, but to the courage of individuals willing to challenge established norms. Lives were saved at sea, not because of mathematical formulas alone, but because someone had noticed what others had overlooked. As the final Victory ships sailed into service, I watched from the yard, the hum of cranes and torches around me. I thought of the Liberty ships, of sailors who had braved brittle steel and freezing seas, and of the small but crucial decisions that had changed everything. Each vessel carried a piece of human insight, a reminder that progress often depends on listening to those who engage directly with the work. The war ended, and the Victory ships continued to serve, some for decades. They carried supplies, rebuilt nations, and helped establish peacetime commerce, standing as monuments to a revolutionary approach to construction, one where observation, care, and precision combined to overcome the limits of speed and fear. By 1946, the Victory ships had become more than vessels. They were symbols of innovation, perseverance, and human insight. The Liberty ships' failures were now lessons embedded in every curve of steel, every weld bead, and every structural frame. Across Richmond and beyond, engineers, welders, and supervisors reflected on the monumental shift in shipbuilding philosophy. Speed alone was no longer the measure of success. Precision, sequence, and the ability to observe were equally vital. Callahan returned to a quieter life after the war. Unlike the headlines and propaganda reels that celebrated shipyard productivity, his contribution was largely unsung. He received letters of commendation from supervisors and occasional recognition in technical reports, but the true impact of his insight rippled far beyond accolades. Every ship constructed using his sequencing methods carried his legacy silently across oceans. Sailors who boarded the Victory ships never realized that the stability underfoot, the resistance to cracking, and the reliability in freezing waters were thanks to someone who had simply noticed how the steel moved under a torch. The industrial world quickly adopted the lessons of Richmond shipyards. Prefabrication, modular construction, and thermal stress management became cornerstones of modern engineering. Offshore oil platforms in the Arctic, pipelines across frozen terrains, nuclear pressure vessels, and bridges all benefited from methods perfected for Victory ship construction. The catastrophic failures that had once plagued Liberty ships were meticulously studied, and every future project incorporated stress relief protocols, weld sequencing, and careful quality inspections as standard practice. One vivid example came in the late 1972 during the construction of the Trans-Alaska Pipeline. Engineers meticulously planned welding sequences, applying annealing processes to critical sections just as the Victory ship program had done decades earlier. The lessons from Richmond ensured the safe transport of millions of barrels of oil through sub-zero conditions, eliminating the risk of brittle fracture that had once claimed liberty ships. In civil infrastructure, bridges became safer thanks to these principles. The Golden Gate Bridge seismic retrofits in the 1990 seconds utilized welded reinforcement based on sequence-optimized stress management, echoing the very techniques first applied to Victory ships. Even catastrophic events like the Point Pleasant Bridge collapse in 1967 and offshore platform disasters in Norway prompted investigators to rediscover the importance of welding sequences and residual stress management practices that had been pioneered during the 1940 seconds. Despite the widespread adoption of his methods, Callahan remained a quiet figure. He never testified before Congress, never published a technical paper under his name, and rarely attended conferences. Yet his impact was profound, woven into the DNA of modern engineering. Students today study failure modes, stress propagation, and thermal contraction, all principles demonstrated through his practical observations in Richmond's shipyards. Victory ships themselves continued to serve long after the war. The Pacific and Atlantic fleets carried supplies, troops, and reconstruction materials, proving the durability and reliability of Callahan's approach. Minor cracks were repaired on-site, but catastrophic failure became a relic of history. Ships that would have disintegrated in a Liberty-class design now sailed confidently through storms, hostile waters, and freezing seas. The sailors who had once feared for their lives aboard brittle Liberty ships marveled at the sturdiness of their new vessels. Oral histories recount the transformation in morale. Crews trusted the ship beneath their feet, operational efficiency improved, and missions were completed with unprecedented reliability. Victory ships became more than cargo carriers, they were lifelines, moving millions of tons of supplies essential to Allied success and post-war recovery. Looking back, the real miracle was never the 5-day construction timeline. It was the willingness to observe, question, and adapt. The courage to halt production, rethink sequences, and prioritize structural integrity over mere speed saved countless lives. Every modular assembly, every preheated steel section, every annealing oven reflected a system built to respect both material and human judgment. Decades later, modern engineers designing skyscrapers, bridges, pipelines, and offshore platforms still rely on the foundational principles demonstrated in Richmond. Computational simulations now replicate thermal expansion and residual stress, but the insights remain the same. Understanding the material, controlling the sequence, and anticipating failure points can prevent disasters before they occur. Bessie Hamill, Callahan's counterpart in the original Liberty ship innovations, had quietly passed in Sacramento, her work acknowledged only in technical commendations. Her name rarely appeared in textbooks, yet every structural welding code, every stress relief procedure, carried her influence. Callahan's legacy paralleled hers, practical observation over theoretical assumption, proving that those closest to the work often hold the key to revolutionary breakthroughs. The Victory ships, born from lessons of failure, from painstaking observation, and from disciplined, human-centered engineering, embodied the very essence of progress. They were a testament to the unsung heroes, the welders, the engineers, the observers whose insight ensured that a ship built in mere days could withstand decades of service. The Liberty ships had been rushed into history. The Victory ships were built to last, measured not by hours, but by the lifetimes of those who relied upon them. In the quiet of Richmond, amid the hum of industrial machinery and the echoes of a war that had demanded everything, the lesson endured. The genius of engineering is not only in design or speed, but in careful observation, respect for material, and the courage to challenge assumptions. Victory ships were not just vessels, they were monuments to that principle, a principle that continues to safeguard lives and structures across the globe to this very day. Post-war America faced a monumental task, rebuilding industries, infrastructure, and global trade routes. The Victory ships, initially designed for wartime urgency, became the backbone of this reconstruction. Ports from Manila to Rotterdam relied on these ships to transport food, machinery, and essential materials. The reliability of the hulls, ensured by meticulous welding sequences and stress relief protocols, meant that supply chains operated without the interruptions that had plagued the Liberty ships. Engineers and shipbuilders who had trained under Callahan and Bessie Hamill's methods became sought-after consultants worldwide. Nations recovering from the devastation of war adopted modular construction and stress management techniques. Shipyards in Japan, Germany, and the United Kingdom began implementing prefabrication and controlled weld sequencing, directly inspired by the Richmond model. The global maritime industry was undergoing a quiet revolution. The Victory ships themselves demonstrated remarkable longevity. Many remained in service well into the 1,960 seconds and 1,970 seconds, ships that had faced rough Atlantic storms, Pacific typhoons, and Arctic cold returned to port with minimal maintenance. The difference between Liberty and Victory ships was evident in both crew testimonials and structural assessments. Where Liberty ships suffered catastrophic fractures under stress, Victory ships absorbed impacts, distributed loads efficiently, and maintained structural integrity under conditions previously thought fatal. Beyond maritime applications, the principles perfected in Victory ship construction began to influence other industries. In aerospace, engineers recognized that thermal stresses and material contraction during welding and assembly could compromise fuselage integrity. Modular assembly lines, pre-annealed components, and controlled welding sequences were integrated into aircraft production. Boeing and Lockheed engineers cited lessons from Richmond as foundational for post-war aircraft manufacturing. Civil infrastructure also benefited. Bridges, dams, and skyscrapers incorporated stress relief protocols during construction. The catastrophic Point Pleasant Bridge failure in 1967, which claimed 46 lives, prompted investigators to study residual welding stress, a problem mitigated decades earlier in Victory ship construction. Retrofitting standards in the United States, Europe, and Asia began to require sequenced welding and thermal stress management, ensuring structural resilience under extreme conditions. The offshore oil industry, which boomed in the latter half of the 20th century, applied Victory ship principles to platforms in hostile environments. Arctic pipelines, subsea installations, and oil rigs relied on pre-stressed modules, controlled welding sequences, and thermal management. Disasters like the Piper Alpha explosion in 1988 highlighted the continued relevance of these practices. Subsequent investigations repeatedly traced failures to the neglect of stress relief and welding sequences that Richmond engineers had rigorously codified decades earlier. Meanwhile, the human element of the Victory ship program gained recognition, albeit quietly. Welders trained in Callahan and Hamill's methods shared knowledge across industries. Apprenticeships emphasized observation, attention to material behavior, and questioning standard practices, echoing the first principle that frontline workers often detect critical flaws before engineers at desks. The concept of practical, observation-driven engineering became embedded in vocational and technical training programs worldwide. Even in modern naval architecture, the lessons endure. Computer simulations now model residual stresses, thermal contraction, and brittle fracture propagation with incredible precision, but these tools are built upon the foundational insights gleaned from Richmond shipyards. The careful sequencing of welds, the modular prefabrication of hull sections, and the stress relief protocols remain integral to shipbuilding, whether constructing aircraft carriers, submarines, or cargo vessels. Victory ships also influenced emergency response and humanitarian logistics. Their reliability allowed post-war reconstruction teams to transport supplies to disaster-stricken regions with confidence. Whether delivering food to famine-stricken areas or evacuating civilians from conflict zones, the structural integrity and dependable performance of these ships proved indispensable. The foresight embedded in every weld sequence literally saved lives, decades after the guns fell silent. Callahan and Hamill, though rarely publicly celebrated, became quiet legends within technical circles. Their insights demonstrated the transformative power of observation and practical knowledge. By bridging the gap between design theory and fabrication reality, they had redefined industrial manufacturing, creating a template that continues to safeguard lives, improve efficiency, and inspire engineers around the globe. In reflecting on Part 9, it becomes clear that the Victory Ship program was more than a wartime necessity. It was an enduring case study in engineering, human ingenuity, and the importance of listening to those who work closest with materials. The steel that had once fractured in Liberty ships now carried generations of lessons, spanning oceans, industries, and decades of innovation. By the 1982, Victory ships had long transitioned from wartime service to peacetime utility, with many repurposed as cargo carriers, training vessels, or museum exhibits. Their reputation for reliability endured, a testament to the revolutionary welding sequences and stress relief practices first developed in Richmond decades earlier. Maritime historians often contrasted these ships with their Liberty predecessors, noting how design flaws and rushed construction had imperiled sailors, while Victory ships carried cargo and lives safely across treacherous waters. In engineering schools, Victory ship construction became a case study in practical problem-solving. Students analyzed the catastrophic Liberty ship failures, examining how residual stresses, brittle fracture, and sharp stress concentrators led to disaster. They then studied the Richmond solutions: modular prefabrication, center-outward weld sequencing, stress relief annealing, and structural redundancy. The lesson was clear. A deep understanding of material behavior, combined with careful observation of fabrication processes, could transform industrial outcomes. Offshore oil platforms, Arctic pipelines, bridges, and skyscrapers incorporated these lessons directly. The structural welding codes, first formally published in 1947, mandated stress relief sequences, interpass temperature monitoring, and modular pre-assembly for critical components. Projects like the Golden Gate Bridge seismic retrofit, Alaska's Trans-Alaska Pipeline, and subsea oil installations were safer, more reliable, and more cost-effective because they followed principles first proven in Victory ship construction. In the corporate world, lean manufacturing, total quality management, and Six Sigma practices also traced their philosophical roots to Richmond. The idea that frontline workers, welders, operators, technicians could observe process flaws invisible to management or engineers became a cornerstone of modern weighting, production theory. Companies that ignored practical feedback risked inefficiency, errors, or catastrophic failure. Those that listened, tested, and adapted thrived. Callahan and Hamel, though largely absent from public acclaim, influenced generations of engineers and fabricators. Callahan's quiet insistence on precise welding sequences and thermal management proved as critical to aerospace fuselages as it had been to ship hulls. Hamel's practical intuition, her courage to question accepted practice, inspired a culture where observation and experimentation were valued as highly as formal education. Together, they embodied the principle that innovation often comes from the shop floor as much as the drafting table. Even decades later, retired sailors and engineers remembered the Victory ships with reverence. Oral histories recalled crossing stormy North Atlantic waters, loading cargo in icy ports, or navigating typhoons in the Pacific. Crews marveled at the resilience of the steel, hulls, the absence of catastrophic cracks, and the confidence it inspired. They understood that their trust in these vessels had been earned through decades of careful engineering and painstaking fabrication practices. The Victory ship legacy also reshaped industrial philosophy. From aerospace to civil engineering, energy production to maritime logistics, the Richmond principles, modular construction, stress relief welding, thermal management, and meticulous sequencing became standard practice. The global infrastructure of the 20th and 21st centuries relied on these innovations, often unknowingly paying homage to a warship program that had begun as a desperate attempt to outpace enemy U-boats. By the early 21st century, museums preserved several Victory ships, allowing the public to witness firsthand the craftsmanship, engineering, and human ingenuity embedded in every weld. Exhibits highlighted the contrast with Liberty ships, the Liberty hulls that had fractured catastrophically, and the Victory hulls that had withstood decades of service, storms, and wartime operations. Visitors learned how a welder's observation and an engineer's willingness to adapt could save thousands of lives and redefine an industry. Ultimately, the Victory ships were more than maritime vessels. They were monuments to problem-solving, teamwork, and courage. They symbolized the triumph of observation over assumption, careful planning over reckless haste, and human insight over blind adherence to theory. Bessie Hamel and Callahan may not have been household names, but their work saved lives, shaped industries, and left a legacy that persists in every welded bridge, offshore platform, pipeline, and modern ship constructed today. The story of the Victory ships is, in essence, a story about engineering, humanity, and the quiet power of paying attention. In a world increasingly driven by speed, efficiency, and numbers, the Richmond shipyards remind us that true innovation often begins with noticing what others overlook and having the courage to act. By the 1970 seconds and 1980 seconds, engineers began to appreciate that Victory ships had accomplished more than wartime logistics. They had rewritten the rules of large-scale fabrication and industrial risk management. The meticulous attention to welding sequence, thermal stress, and structural redundancy was not just a maritime lesson. It became a cornerstone for nearly every industry working with large welded structures. Nuclear power plants, for example, relied heavily on lessons first proven in Richmond shipyards. Reactor pressure vessels, designed to withstand extreme temperature fluctuations and internal pressures, required precision welding and stress relief treatments. The failure to implement proper sequencing, engineers realized, could lead to cracks propagating through critical components, mirroring the Liberty ship disasters decades earlier. Victory ship methods provided a proven, field-tested template. In aerospace, commercial aircraft and military jets benefited from the Richmond principles. Aircraft fuselages, subject to extreme pressurization cycles, underwent strict modular assembly and controlled welding sequences to prevent residual stress accumulation. Boeing and Lockheed engineers openly cited Victory ship techniques in internal training and procedural manuals, highlighting how a practical wartime innovation had influenced peacetime design standards. Civil infrastructure projects likewise adopted these lessons. Bridge construction, high-rise steel frameworks, and offshore oil platforms incorporated stress relief and thermal management protocols. Catastrophic structural failures, like the Point Pleasant Bridge collapse of 1967, were traced in part to the neglect of residual stress management, a problem Victory ships had solved decades earlier. Engineers learned that even minor deviations from prescribed welding sequences could propagate cracks rapidly in brittle conditions. Beyond structural engineering, Victory ships inspired new approaches to industrial management. Lean manufacturing, total quality management, and Six Sigma all emphasize the integration of observation, real-time feedback, and procedural discipline principles first demonstrated in Richmond. Workers on the shop floor, empowered to report potential flaws or inefficiencies, became a critical part of the quality assurance process. Observation-driven engineering, exemplified by Bessie Hamel, became a foundational teaching in vocational programs worldwide. The human impact of Victory ships was equally profound. Merchant mariners, once fearful of Liberty ship fragility, gained confidence in these redesigned vessels. Morale improved, operational efficiency increased, and the logistical capabilities of the U.S. military expanded dramatically. Oral histories recount how crews felt empowered to push ships to their design limits, knowing that each weld and stress relief procedure had been optimized to prevent catastrophic failure. Victory ships also became a symbol of the collaboration between engineers and frontline workers. The Richmond shipyards demonstrated that innovation often originates from those who directly interact with materials, tools, and processes. Hamel's insight, derived from careful observation of metal behavior under heat, showed that practical knowledge could surpass theoretical assumptions. This principle resonated across industries, emphasizing the importance of inclusivity and communication in engineering design. In education, Victory ship construction became a staple case study in mechanical, civil, and materials engineering curricula. Students analyzed how welding sequence, residual stress, and structural redundancy could influence long-term performance. They learned that even state-of-the-art designs could fail catastrophically if fabrication methods were mismanaged, a lesson that remains relevant in modern engineering projects worldwide. By the late 20th century, the Victory ship methodology had been fully codified into international welding standards. Stress relief sequencing, interpass temperature monitoring, and modular prefabrication became mandatory for critical infrastructure. Offshore oil rigs, Arctic pipelines, high-rise buildings, and naval vessels all relied on principles first proven in Richmond during the 1940 seconds. The legacy of Victory ships extended far beyond the Atlantic and Pacific, influencing global engineering practice in fundamental ways. Even in the 21st century, the Richmond innovations continue to resonate. Advances in computer modeling, finite element analysis, and automated welding systems are built upon foundational lessons from Victory ships. Modern engineers simulate residual stress, thermal contraction, and brittle fracture propagation before a single weld is struck, practices that Bessie Hamel first implemented intuitively in 1943. Her legacy persists, a quiet but enduring influence on every welded structure in the modern world. Victory ships also shaped industrial philosophy. Speed alone, it became clear, was insufficient. True industrial excellence required balancing efficiency with precision and theory with observation. The courage to halt production, re-evaluate processes, and implement practical insights, even when they contradicted established engineering assumptions, became a guiding principle for complex project management. Ultimately, Victory ships are remembered not just as vessels of steel, but as vessels of knowledge. They embody the triumph of human observation, ingenuity, and collaboration over theoretical blind spots and rushed construction. Bessie Hamel and Callahan's contributions may have gone unheralded in popular history, but their influence underpins modern engineering, safety standards, and industrial efficiency worldwide. As the 21st century progressed, Victory ships remained a tangible reminder of the power of observation, innovation, and disciplined fabrication. Several surviving vessels were preserved as museum ships, allowing engineers, students, and the public to witness firsthand the precision and care embedded in every weld. Visitors could see the subtle differences in hatch corners, the smooth, evenly stress-relieved plates, and the modular construction that had once allowed an entire hull to be assembled in mere days without catastrophic failure. Historians noted that the Victory ships represented a turning point in industrial philosophy. They demonstrated that large-scale production could be fast, efficient, and reliable if human insight guided the process. The lessons of Richmond shipyards transcended maritime construction. Across industries, from aerospace to energy, from bridges to pipelines, engineers applied the principles of sequenced welding, stress relief annealing, and modular prefabrication to improve safety, reliability, and longevity. Victory ships also highlighted the critical role of the workforce in driving innovation. Hamel and Callahan exemplified the principle that the people closest to the work often have the clearest understanding of practical challenges. Modern manufacturing, lean production, and quality management systems all echo this insight, emphasizing feedback loops, worker empowerment, and continuous improvement. In many ways, the ship's success was as much about human collaboration as it was about steel and welding torches. The impact of Richmond's innovations was visible in every high-stakes project where failure could be catastrophic. Offshore oil rigs, nuclear reactors, subsea pipelines, and high-rise structures all depended on the careful sequencing, stress management, and quality control pioneered in Victory ship construction. Each weld, each annealed section, and each stress-relieved plate carried forward the lessons learned in 1943–44, decades before computer simulations and robotic welders became standard tools. Even beyond engineering, Victory ships became symbolic. They represented the courage to question assumptions, the patience to refine processes, and the discipline to marry speed with quality. They reminded future generations that revolutionary ideas could come from the most unexpected sources: a night shift welder, a meticulous engineer, or a frontline observer. Innovation was rarely linear. It required attention, experimentation, and the humility to recognize when conventional wisdom was wrong. By the early 2022s, victory ships were not just historical artifacts, they were living textbooks. Maritime academies, industrial training centers, and university engineering programs used them to teach complex concepts: thermal expansion, residual stress, brittle fracture, modular assembly, and quality assurance. Students learned that theoretical knowledge alone was insufficient. Observing, testing, and adapting in real-world conditions was equally vital. Bessie Hamel and Callahan's legacies endured quietly but powerfully. They had transformed a wartime necessity into a permanent industrial revolution. Every modern welded bridge, every pipeline across frozen tundra, every offshore platform braving stormy seas, and every large-scale modular assembly benefited from their insights. Their work proved that courage, observation, and meticulous attention to detail could ripple across decades, industries, and continents. In retrospect, the true achievement of victory ships was never merely their speed of assembly, it was their reliability, resilience, and the human ingenuity embedded in every structure. While Liberty ships had been a stopgap, fraught with catastrophic failures, victory ships became enduring benchmarks of industrial excellence. They demonstrated that the marriage of practical insight and scientific understanding could create structures capable of withstanding both the elements and the pressures of human expectation. Ultimately, the victory ships stand as monuments not of steel alone, but of human intellect, observation, and courage. They remind the world that even in times of crisis, listening to the front line, respecting practical wisdom, and systematically applying lessons from failure can save lives, shape industries, and leave a legacy far beyond the original mission. The Richmond shipyard story is thus a testament to the power of noticing what others overlook, acting on that knowledge, and transforming an entire field. Every weld laid with care, every stress-relieved plate, every modular assembly, and every perfectly aligned section carries forward the lesson that innovation is most profound when it unites the human mind with practical reality. Victory ships were more than vessels. They were symbols of enduring engineering excellence, proof that meticulous observation, courageous problem-solving, and disciplined execution could change the world one weld at a time. Beyond steel, welding, and industrial techniques, victory ships also left a profound mark on the human experience of war and work. Sailors who had previously feared Liberty ships for their fragility felt a renewed sense of confidence aboard these resilient vessels. Merchant mariners, many of whom had endured the psychological strain of watching ships split apart in cold Atlantic waters, now reported reduced anxiety, better sleep, and a sense of pride in their work. The morale boost translated directly into operational efficiency, faster turnarounds in ports, and increased willingness to sail through adverse weather and hostile territories. The story of victory ships also highlighted the importance of diversity and inclusion in industrial problem-solving. Bessie Hamel, a woman on the graveyard shift in a male-dominated shipyard, challenged established engineering assumptions and revolutionized construction processes. Her contribution exemplifies how diverse perspectives, particularly from frontline workers, can uncover overlooked flaws and spark transformative innovation. It became a quiet but enduring lesson. When organizations listen to all voices, they unlock insights that formal hierarchies often miss. Victory Ships' legacy also reshaped industrial training programs. Shipyards, manufacturing plants, and engineering firms worldwide began to emphasize the value of practical observation, continuous feedback, and iterative problem-solving. Training curricula shifted from purely theoretical approaches to hybrid models combining classroom knowledge with hands-on experience. Workers were taught to detect subtle signs of material stress, recognize anomalies, and apply corrective sequences skills that trace their lineage directly back to Richmond Shipyard's methods. The ships themselves became educational platforms, Museum ships and preserved vessels offered tangible demonstrations of modular assembly, stress relief welding, and crack arrest mechanisms. Visitors could observe firsthand how carefully sequenced welds and prefabricated modules combined to form structures that were both robust and efficient. Each Victory ship served as a living classroom, bridging past innovations with modern engineering principles. Victory ships also influenced national policy and wartime planning. The success of the Richmond shipyards demonstrated that large-scale industrial projects could balance speed, cost, and quality if carefully managed. Government agencies incorporated these lessons into future procurement and infrastructure programs, ensuring that lessons learned under the pressures of war would improve peacetime industry as well. On a cultural level, Victory ships became symbols of resilience and ingenuity. They represented the triumph of meticulous observation and courage over hurried assumptions and systemic failure. Stories of crews safely navigating Arctic waters, surviving kamikaze attacks, or transporting critical supplies under extreme conditions became part of the shared wartime narrative. Unlike Liberty ships, which were often remembered for their fragility, Victory ships were celebrated for their reliability, strength, and the human ingenuity embedded in every weld. In modern times, the influence of Victory ships is evident in advanced robotics, automated welding systems, and computer-modeled fabrication techniques. Engineers now simulate thermal expansion, residual stress, and fracture propagation digitally before construction begins. Yet the principles remain the same. Sequence welds to distribute stress, modularize construction for precision, and combine observation with rigorous testing. Every contemporary high-stakes project, from nuclear reactors to offshore platforms, owes part of its methodological foundation to the lessons first codified in Richmond shipyards. Ultimately, Part 13 underscores that Victory ships were not just engineering triumphs, they were human triumphs. They showed how careful attention, disciplined procedures, and respect for frontline knowledge could save lives, preserve cargo, and change industries. The story of Victory ships is a reminder that even in the midst of war and immense pressure, innovation thrives, where observation, courage, and meticulous execution intersect. In early 1943, Liberty ships were America's lifeline, meant to ferry vital supplies across the Atlantic. Yet, despite rapid production, disaster loomed. Ships like the SS Schenectady split in half under calm conditions, not from enemy attacks, but from structural failures. Sailors feared the hull beneath their feet could fracture at any moment. More than 2,500 Liberty ships suffered serious cracks, some disappearing entirely at sea. The root cause eluded engineers for months. Steel met specifications, welds appeared solid, and designs came from proven blueprints. Yet, catastrophic failures persisted. The problem lay not in material, but in construction. Welders followed a seemingly logical sequence: long seams, edge-to-edge welding, finishing sections as quickly as possible. But as each weld cooled, the steel contracted, creating residual stress that accumulated across the hull. Cold North Atlantic waters made the steel brittle. Sharp corners at hatches and gun mounts acted as stress concentrators, allowing microscopic cracks to explode into devastating fractures. The breakthrough came from unlikely sources. Bessie Hamill, a night shift welder at Richmond shipyards, observed how steel warped during welding. She experimented with different sequences, discovering that starting at the center of a section and welding outward allowed stress to dissipate naturally. She also found that alternating weld locations and avoiding long continuous seams prevented heat buildup. Her foreman initially dismissed her, but Hamill's persistence convinced supervisors to test her methods. The results were undeniable. Residual stress dropped dramatically, and steel distortion virtually disappeared. Henry Kaiser, the industrialist behind mass-production shipyards, faced a choice. Liberty ship program was under scrutiny, but he could either continue producing fragile vessels at record speed or adopt Hamill's method, retrain welders, and redesign ships. He chose the latter. The result was the Victory ship, a fundamentally improved vessel built with sequenced, stress-relieved welding, modular prefabrication, and rounded structural corners. The transformation was remarkable. Modules were prefabricated in controlled environments, then assembled with precision. Sections underwent stress relief annealing, and welders followed strict sequence cards. Quality control intensified. Every weld received magnetic particle, ultrasonic, and X-ray inspections. Initially, 15% of welds failed, but by mid-1944, rejection rates fell below 3%. Production speed remained impressive, but more importantly, the ships were safe. The SS Benjamin Warner, for example, was fully built in just over 5 days, complete, combat-ready, and free of cracks. Victory ships' reliability revolutionized wartime logistics. Between June 1944 and August 1945, 531 ships were launched with 0 catastrophic hull failures. Crews sailed Arctic convoys, braved kamikaze attacks, and transported millions of tons of cargo with confidence. Unlike Liberty ships, Victory ships combined speed with safety, proving that industrial efficiency need not sacrifice human lives. Beyond the war, the lessons endured. Weld sequencing, stress management, and modular construction influenced pipelines, bridges, nuclear reactors, and offshore oil platforms worldwide. Richmond shipyards demonstrated that frontline observations could drive monumental engineering breakthroughs. Bessie Hamel's insight, though unheralded, shaped modern welding codes, manufacturing training, and quality assurance standards. Every welded skyscraper, pressure vessel, and Arctic pipeline traces its lineage to those innovations. Victory ships symbolized more than steel and speed. They represented ingenuity, courage, the power of human observation. They proved that careful attention to process, respect for practical knowledge, and disciplined execution could overcome systemic failure. Where Liberty ships had been fragile stopgaps, Victory ships became enduring monuments to engineering excellence, saving lives and reshaping industrial methodology for generations.